Okay, let's see. Where were we? So during the break, I actually continued running this code, and you can see that we were looking at the new biggest avalanche. So always we saw some big events, but that's not the case, of course. Let's see. This is the potential before, and this is the tiny avalanche, and you can see that potential is more or less unchanged. Do you see? So let's see another run. Here, that potential, I mean, the grain actually gets to that place and the potential is unleashed. I will keep using that word. Uh, but do you see that it's not gone forever? Uh, the stress actually remains around there, it just changes the shape. So what about here? For example, it remained the same except for some potential going out here, or over here, something like this. Okay, so I was going to look at the paper, right? I think. This is the original paper. Now, we haven't connected this with the main question, right? Where is physics? How it connects to fractals? Well, and how it connects actually to 1 over f noise. So Perbach did the following, and his friends. Let's make a histogram of avalanches, like how many size 10 avalanche happened, how many size 20, how many size 30, 40. You can see that it could be 1 to 3 and also 232,563. Did you see that? Like you can have huge avalanches and small avalanches. Well, if you actually plot the frequency of the avalanche versus the size of the avalanche in a log-log plot, you get a line, a single line. So all the data falls into a straight line, except for this one, which is finite size effect. So if you had bigger cells, like here it's 50-50, right? So normally it would go on forever, but it has to stop somewhere because you can't have that big event in a 50-50 cell. Do you see what's going on? Let's actually watch it closely. So this line has so many implications. One of them is that the tiniest events are totally connected to the largest events, the biggest events. Okay, that's one. Two, you don't need any external intervention to get huge events. The system itself, via the small events, can self-organize to criticality, which creates big events. Okay. Another implication is that catastrophes are inevitable, right? Even if you take into account everything, if the system in itself has this inherent drive towards criticality, okay, then you will have also huge catastrophic events, explosions. What else? Okay, fractals. Now, just imagine, do you remember how we defined fractals? Do you remember what we used? To find the dimension of fractals, we said that if you have, for example, a point around it, as you increase the radius, you engulf more and more points, but it goes with r to the dimension of the fractal, right? Here, just imagine So you can see that it's totally analogic to earthquakes, right? If you don't see that, maybe I have a paper here. Maybe you can read this paper. Self-organized criticality in a continuous non-conservative cellular automaton modeling earthquakes. Year 1991. Okay, so this concept is used in many places. And let me start talking about it. But first, again, let me make the point that it explains fractals, at least the geographic ones, because you have a big event and it leaves some signature on the landscape, the big one, right? But they are less frequent, logarithmically less frequent than the small events. Small events occur much more, and they will keep patterning that landscape, and eventually you will get a fractal shape. Does it make sense to everyone? Yes? I hope so. If you want to know much more about self-organized criticality, I recommend you to read this book by Per Buck himself, How Nature Works. Okay? So the book starts with this prophetic sentence. How do we know that the creations of worlds are not determined by falling grains of sand? You see? Uh, then another thing about self-organized criticality is that the state that you eventually reach has no scale. It's scale free, just like fractals. If you scale in it, you would see the same complexity, right? In the same fashion, uh, the systems that are self-organized to criticality don't have scales in time or space, because just imagine the duration of avalanches. Okay, the big events will uh, endure for longer time, but they will be less frequent. Okay, earthquakes. What about game of life? Actually, Perbach tried, this is one of his nature papers. He showed that this can be one of the projects. It's okay if you reproduce this, it's a good project. Uh, he has shown that if you perturb game of life, just like we do in the sand model, it will self-organize to criticality. Okay, where like one perturbation would create avalanches of all sizes. Does it make sense? What else? Uh, if we deviate a little bit from the topic, Chris Langton, you did his ant without knowing that you are doing his ant in homework one. Do you remember this thing that was walking towards right or left, etc.? That's Chris Langton's creation. Okay, it's called Langton's ant. So, and this is one of the most important papers of him. So here he actually analyzes all possible, not all possible, like many different automata. Just remember the rule 30, the rule 110. There you had cells and you would interact with its neighbors, right? But what if you can interact with other neighbors too? And what if you develop the models, try different things? He wanted to combine all this in a single parameter lambda. And he did it the following way. Let's say you choose a set of rules. Then you calculate what is the probability of getting one in the next step. Okay, that's lambda. Okay, so you can see that if lambda is small, you quickly stop, right? If lambda gets bigger, you have this something like fixed point. If it's even bigger, maybe something like a limit cycle. If it's even bigger, and especially at the point where it reaches 0.5, you have uh, the system is at criticality. as critical as it is possible, because you have finite number of sites. Eventually it will start repeating itself, but you can see that here it is doing something uh, like lifelike. Do you see, everyone? Then as you keep increasing lambda, you get into the region of chaos. Okay, so basically uh, remember our point today was like, or this in this chapter, like life is critical, and self-organized criticality is a good mechanism for life to self-organize itself into criticality, where it has scale freeness. Especially scale free in time is very important. You can, like, uh, living organisms can be as like maximum adaptive that way. Okay, it's basically something like life is between two deaths. One of them is static death, and the other one is dynamic death. Like, are you following? And life is in between. And self-organized criticality makes such a system where the arrows actually point at life. Well, actually, Perbach didn't stop there. That's why he wrote this book, uh, How Nature Works. He applied this self-organized criticality idea to river networks, traffic jams, okay, brain activity, punctuated equilibrium. Have you heard of it? You? Have you heard of it? And maybe Bishra would have heard of it. It's one of the important points of the evolution theory. So basically, it's very hard to find the when if you look at the fossil data, suddenly one animal turns into another. It's not like a slow transition. It appears very fast. Okay, and actually, believe it or not, Perbach came up with the simplest model I've ever seen in any system. Okay, and I will explain it in a moment. Let's look at, I forgot to mention Lioka Donald himself, who asked, where is physics? It's important to ask questions, okay? And you can see that he himself contributed to fractal science. It's not like he doesn't like it. Let's look at Perbach. So this is self-organized criticality, how nature works, okay? And the next best thing that he did is this punctuated equilibrium and criticality in a simple model of evolution. Are you with me? Yes? So let's look at that paper. This is the paper. And there are so many nice parts. And in the previous lecture, I couldn't find uh, the sentence. Do you remember? I actually found it. Let me read it for you. Metropolis's paper. I hope you are able to follow when I do this. Okay, so this was the sentence, and the problem was that part of it is here and part of it is on the top of the page, so that's why I couldn't find it. Now, for a moment, switch back to Monte Carlo method. So the method we employ is actually a modified Monte Carlo scheme, where instead of choosing configurations randomly, then weighting them with e to the minus e over kbt, we choose configurations with probability e to the minus e over kbt and weight them evenly. That was the brilliant sentence. Now let's come some brilliant sentences in this punctuated equilibrium paper. Let's find them. life is synonymous with volatility and evolution rather than stability and fitness. Okay. So what he means by this, let's actually talk about the model. So I think he's apologetic enough in the paper to justify his simple model. So basically the model, and you can please read this paper, okay? It describes much more of the points that I'm going to make. So he thinks of the organisms as a network. It could be a food chain or something, or just proximity, whatever. And each one of them has fitness. Okay, the system starts, so n numbers around the n sites around the circle, and each one starts with random number. Okay, between 0 and 1. Then you choose the one with smallest fitness, okay, and replace it with a random number. Okay, so let's say this one was 0.1 and it was the weakest one. You replace it with any random number. Just tell me any random number between 0 and 1. 0.5. But you don't only replace this one, you also replace its neighbors. Why is that? Can you? Well, think of all these sites as species, actually, like all mice, all birds, all whatever. But they are interacting with each other. So if you replace the fitness, by the way, I'm skipping many parts. By replacing fitness, they are talking about mutation. Okay? So if you mutate an organism that other organisms depend on, right? Then their fitnesses also has to change. Do you understand what's going on? Yes? So what you do is you choose the minimum one, you replace it with random number, and you also replace this one with random numbers. Okay, that's it. You have to stop somewhere, right? But in the next run, there is so let's think if this wasn't the case, if the organisms didn't interact, what would lead? What would be the ultimate product of changing the weakest ones with random numbers? What would be the ultimate case? No. Yes. That's our idea of evolution. Everything just becomes stronger and stronger, right? But that's not the case. I mean, if you just replace the weakest one with random number, weakest one with random number, all of them will increase in fitness until they reach 1. Okay? And every time you will change someone at random, but you will change it lots of times, and it will again become 1, very close to 1, and the other one will change. But if you allow interaction, which you should, then the system actually does something much more interesting. Did you follow all these arguments? So let's see the model. It's still running. That's why I have this fan going on. You are convinced about this, right? So I will stop running. Maybe this one is nice. So number of species, right? Number of evolutionary epochs, right? This is initial fitness. These are 3 random numbers that you need numbers for each epoch. You need them, right? And what is this? S? Okay, I don't think it's something useful, so I will just erase it. So this one, find the weakest. Yeah, sorry. Just find the weakest. Replace weakest and its neighbors. Plot fitness. There is an SF here. Yes, we are not using it, so let's just dummy. Are you happy? Thank you. So we are going to plot them, and let's actually start. So they will quickly organize, and maybe not so quickly, but eventually they will organize at a so we imagine that without interaction everybody would be like, okay, let's repeat this one, but I want to change some stuff. So I want to to 20. Fitness is this one. What do you mean by fitness? Okay, that's a very nice question. Can you tell me what fitness is in evolutionary sense? Yeah.
Choice that will result with the most of your copies.
What?
The result that will, the effect that will result with the most of your copies.
Yes. So, all of the above. So you answered your own question. So that number corresponds to how fit you are given the certain landscape. It's okay. Normally these things are done in the following way. So you assume that each one has actually a gene, an array of zeros and ones, for example. And okay, read the paper, it talks about it a lot. Now I realize that I don't understand it, but fitness itself, okay, it's just a number, an accumulated number of all of the above, like how fast it reproduces, what are the chances of it getting killed, etc., etc. I'm not sure I'm answering your question or not. It's not something that corresponds to anything real. Was that the question? They don't model it, okay? They just say that, let's say we modeled it. It's just after a lot of modeling, you will get one number, right? How fit are the mice? How fit are the mice? Sorry, very bad English. How fit are the horses? All of them living in Africa, for example. How fit are they, given the environment? Okay. Then, if, for example, all horses depend on what horses eat, let's have something that eats another animal. Like all lions depend on rabbits, and suddenly they eat too much of them, okay, and they are gone, or they are the weakest ones, so we mutate them. They become faster runners. What happens to lions? Their fitness also decreases. Or it might not decrease, it might increase. We don't know. That's why we actually replace the numbers of the weakest one with the uh, random number. I'm not sure if I gave you the answer, but okay. Let's do the following. Is it boring? Okay. Uh, Let me plot this one first. This is too much, sorry. Maybe this much. So this is a better picture. So now we are watching in the, this is horizontal is time, and these are the species. And the dots are the points where we had differences, okay, where we had modifications. You can see that there are these huge events, which, according to him, according to Perbach, corresponds to this punctuated equilibrium. Suddenly, uh, like Cambrian explosion type of changes. Okay, and he says that you don't need necessarily a meteorite to drive those changes. Those changes can be intrinsic in the system, already present in this in itself, because the system drives itself there through interactions. And once we reach that point, we run it for a long time. So let me plot now the fitnesses. Uh, this is not what I expected to see. I had a better picture. Let me see. Do you have any questions so far at this point? No questions. Let me run this one. Okay, this is way better. So what I'm plotting here, let me understand. What am I plotting here? I'm plotting the minimum fitness that I chose each time. Are you following? The minimum fitness I chose each time. Do you see that it doesn't go above some critical point? Do you see? 0.67. At first they thought that it's, of course, it's 2 over 3, but it isn't. It's actually some number that can be derived analytically. But the system, so, and this critical point actually emerges from interactions. Are you following? Yes? And if you had no interactions, then that point would go to 1, very close to 1. Do you agree? Everyone? Okay, that's the main point that I wanted to make. And then if we come back to the paper, you can see that they also do something like related to, so yes, it's fitness, but it's also uh, the barrier for mutation. I will explain it in a moment. Are you following? Everyone is with me? Yes? So let's choose the weakest organism, okay? What is the barrier for it to become better? It's lower than the fit one. Did you follow this?
Yeah.
Did everyone follow this? So if you have a very fit organism, then to make it even fitter involves much more mutation than an organism that is already weak. Because by chance you can make a weak organism strong. So this fitness also corresponds to the number of mutation needed to be better. Okay, and here, like, this is the plot that we also made. Do you remember something like this in our plots? But then they turn it into this plot. How they do it? They say that if the barrier is low, then the change will occur in shorter time. Okay? Oh, okay. Sorry. So exponentially shorter time, actually. So if you include that modification, then it looks much more like punctuated equilibrium, because you come here, nothing happens, suddenly something happens. Okay? So you can, and also they have, of course, log size of the event, log probability of the event, okay, and they fall into line, just like in self-organized criticality, which means that it has also the same messages. All sides of events are connected to each other. You can have catastrophes even though you take all precautions. Okay, the system in itself drives itself to criticality. Okay, are you with me? Then he went on democratic reinforcement, a principle for brain function. You should read this. I will not talk about this. And he started something. He started thinking about the brain being self-organized into criticality, and especially this person, Chialvo, maybe, Argentinian scientist, took it to the next level. He is carrying this flag of, like, brain has to be critical, flag, and they have some model that they compare with actual fMRI data, and when their model is tuned to criticality, it's not self-organized. If it's tuned to criticality. Do you remember what criticality was in Ising model? It was the place where you go from order to disorder. So right there, the brain, the model images look very similar to fMRI images, but below and above criticality, they don't look like that. So brain in its resting state is a system at criticality. That's the idea. And this idea is seen in many places. Again, you can see Chialvo here. Large-scale signatures of unconsciousness are consistent with the departure from critical dynamics. So if you depart from criticality, you become unconscious. Okay, actually criticality is the place where you maximize information processing and information integration. You can see these things in so many different publications. Like, consciousness may be the product of carefully balanced chaos, a fundamental theory to model the mind, etc., etc. You can see that they even made the joke of sands. Do you see? Yes. Okay, and there are ways to. Do you remember that at that particular paper they actually tuned it. So there's a way to tune the brain to criticality. And let's talk about it once we start talking about the brain. All strings attached. Do you remember that chapter? We will come here. What else I wanted to show you? This last slide. This is the last page from his book. Okay? Let's read this last page. The critical state with jams of all sizes is the most efficient state. Okay? So he's talking about traffic jams, right? The system has self-organized to the critical state with the highest throughput of cars. If the density were slightly less, the highway would be underutilized. If the density were slightly higher, there would be one big permanent huge jam absorbing a fraction of the cars. In both cases, the throughput would be less. Do you see the point? Now let's continue. More precisely, the critical state is the most efficient state that can actually be achieved or reached dynamically. A carefully engineered state where all the cars were moving at velocity 5 would have high throughput, but it would be catastrophically unstable. This very efficient state would collapse long before all the cars became organized. So think of all cars moving with... You always have that idea, right, in the traffic jams. Why not move at the same speed, right? Then there will be no traffic jam. But then the system becomes extremely catastrophic. If someone just breaks the law, deviates from the law, right, then you have all cars will crash into each other. We were talking about traffic jams, right? How did we get here? This gives some food for thought when applied to economics in general. Maybe Greenspan and Marx were wrong. The robust state for an economy could be the decentralized, self-organized critical state of capitalistic economics, with fluctuations of all sizes and durations. The fluctuations of prices and economic activity may be a nuisance, in particular if it hits you. But that is the best we can do.
Let people do what they want. Let everyone do what they want.
Yes.
So that Bitcoin thrives.
Yes. I think he would appreciate Bitcoin a lot. The self-organized critical state with all its fluctuations is not the best possible state, but it is the best state that is dynamically achievable. That's the message here.
This is something horrific.
Horrific, right? You can't avoid catastrophes. Okay. Do you have any questions? You have a question.
The pictures that you have shown in the paper, the two pictures about the state changes.
Which paper?
The evolution.
Okay.
Yeah,
this one.
Yes. So what were they showing actually?
Okay. And what are the axes, right?
Yes.
So x-axis is the species. Which species? Like 1 to 64. And this is the time. So this means that we change some species over here, then some over here. And this is the same plot as this one, the same data, but instead of using count time, they use real time in a sense that if the mutation is huge, then it would take exponentially more time than compared to lower mutation. So let's say you choose you choose to replace an organism with fitness 0.1. Remember, after some talking we said that fitness is also equivalent to mutation barrier, right? So 0.1 means that organism has actually lower barrier.
Yes.
and the mutations it needs are low compared to others, actually they are in the real time, the probability of those mutations happening is exponentially less than the others. What do I mean by exponentially less? It goes with the probability of e to the minus, where is it? Okay, I couldn't find it. E to the minus fitness divided by some temperature or some alpha. Does it make sense? Since you are always changing the weakest ones, whenever you make the small change, it takes very little time. Okay? But the big changes take a lot of time. So that's why suddenly something turns into something else and then stays that way because it became fitter, much fitter, right? So before it hits a nice fitness, right? The process will be very fast compared to others. That's why it will be punctuated equilibrium, like this. Of course, it's a model, and I wouldn't say that everybody agrees with this. So this butterfly is not fit at all, let's say, and it needs a few mutations to become fitter, right? So few mutations happen in shorter time. Then this one, to become better, it needs much more mutations. So it stays that way for a much longer time, exponentially much longer time.
This is a very, very simple model.
Yes.
So I'm just wondering, let's suppose, because we said T number of epochs, right? T number of evolutionary cycles before something happens. And during that time, the species somehow is immortal. So I'm waiting till I mutate, right? To become more.
No. It's you look at the whole species and the whole its babies and the whole thing as a single dot.
Yes.
So you are not waiting.
Like here. So we have the lions and the rabbits, right? So the lions keep eating the rabbits. The rabbits say that I'm not fit enough. We need to speed up. But this mutation, they cannot control the mutation. Mutation is due to environmental factors, right?
Who controls mutation?
Random mutation is random. Generally.
So, for example, this
No, he didn't ask the question. Let him ask the question. Okay.
Yeah, so mutation is spontaneous in nature.
Spontaneous, yes.
Right? It just happens.
Yes.
The time taken for the mutation, if it exceeds the lifetime of the species.
Mutation always exceeds the lifetime of the species. It is about 10, 20 generations mutation, or even more.
I'm just imagining the lions come in, they eat these rabbits. The rabbits won't have.
Well, the problem is that you can't imagine million years. You have to, if you are thinking about evolution, you need million years, billion years. Like it formed, like single cells formed 3.8 billion years ago. When did multicellular life came? Okay, let's say 130. I mean, if you look at the relevant pictures, they always show this, or I can't pronounce the channel's name, Kurzgesagt, something like that. They show these changes, right? Like billion years, then million years. So it's a very slow process.
If you think like, for example, a very fit group, let's say 100 of them, so for the next generation, 90 of them survive, 10 of them don't survive. So 90% is a very big number. So the average won't change that much.
Yes.
But if it's not fit, let's say 90% of them die, so we only have 10 of them, so that's a bottleneck. Like it's going to evolve, get mutation a lot more than the other fit ones because you're only getting like very few of them. And the next generation and next generation. So just logically, if they are not fit, they are going to go through the mutation task this way.
Mutations are genetic.
They are independent events. No, they are genetic, but nobody is going into the DNA, reconfiguring it.
No.
There's a less, let's mutate them faster. This is like completely.
No. The effect of the mutation. They will become faster. They will become fitter faster. This is the thing. Or not like mutation is engineered. No.
The fact that we are assuming mutations will become faster.
No, we don't assume that.
No, it does come faster in this sense.
No, I actually, I'm not sure if I agree or understand your point, but the point is that if, let's say, mutation is the same, like rate of mutation is the same, what changes is the rate of change in the fitness because of the mutation. So if you are already not fit, then you can become fit from random mutation with more probability. Does it make sense?
But for example, let's think like raising crops.
Yes.
Like if you want, for example, get bigger corn, you always choose bigger corns.
Yes.
And for example,
that's, by the way, human controlled.
10% would be good. That way you can go to the faster to the position of finding a very big corn. But if you're always mixing every one of them, like 90% of them, you will probably never get a very big corn. So that's what I'm saying. If you're not fit, you're only going to choose the survivors, which is 10% of them, and you will get a bottleneck. Like it's going to be.
I see what you mean.
Same type of mutation in animals, but in the society sense, they will go to a different path a lot quicker.
Yes. What you were going to say?
I was going to say, I think the missing part here is, like, not missing part in the model, missing part in the understanding that we have random mutation, but we have also natural selection. So that's what defines speed in this case. Like, we have still same rate of mutation in every species, let's say, but we have natural selection. So when we combine natural selection and random mutation in genetics, then we have speed acceleration.
Yes. Natural selection is faster in weaker organisms. That's the point. So I hope this lecture made sense to you.
Made sense. I just want to.
Please try reading this paper.